You know, back in the early 20th century, physics got completely flipped on its head. An equation came along that could describe the atomic world with just, stunning accuracy. But hidden deep inside it was a number that mathematicians had basically called impossible, the imaginary number I. So the big question is, what is this supposedly imaginary number doing at the very heart of our reality? Let's dive in and unravel this mystery.
Okay, so picture this. It's 1926 and Erwin Schrödinger drops a series of papers that just completely reshape physics as we know it. His equation basically took over from Newton's laws when you get down to the subatomic world. But it came with this one little feature, a feature that puzzled even Schrödinger himself.
So if you look at Schrödinger's equation, it kind of looks like other wave equations you might have seen. It's designed to show how a particle's, matter wave evolves from one moment to the next. But right there, at the very core of what makes it change, is something that just shouldn't be there. Something that isn't supposed to exist in the real physical world. The square root of -1. Yep, the imaginary number I.
And that right there, that's the central mystery we're tackling. How on earth does one of the most successful theories in the history of science depend on a number that supposedly doesn't even exist in the real world? Well, to find the answer, we have to go back to the idea that sparked this whole thing in the first place.
See, before Schrödinger could even begin to write his equation, the entire world of physics had to get its head around a truly radical, kind of mind-bending idea. The idea that solid matter could behave like a wave.
The whole journey really kicked off with light. So, in 1905, you have Einstein and Planck who figure out that light comes in these little discrete packets called photons. Okay. Then, fast forward to 1924, and this French physicist, Louis de Broglie, he makes this incredible leap in his PhD thesis. He basically asks, hey, if waves like light can act like particles, then what if particles like electrons can act like waves? Well, Schrödinger read about this, and he became obsessed.
And that's the core concept right there, the matter wave. The big idea is that every single particle has a wave associated with it. Now, the story goes that a colleague of his basically challenged him, saying something like, look, if these matter waves are real, there has to be a wave equation for them. And for Schrödinger, that was it. He knew exactly what he had to do next.
All right, so armed with this completely revolutionary idea, Schrödinger set out on his quest to find the one equation that could describe these strange new matter waves.
So he goes and takes a winter holiday up in the Swiss Alps. But this was no vacation. He brought his books, his papers, and a single-minded focus. His goal was singular: discover the fundamental equation that governs the wave-like nature of matter itself. So what was his method? Well, he started with something familiar, the classical wave equation. But then he did something incredibly clever. He started modifying it, weaving in de Broglie's new idea about matter waves, and figuring out how to connect the wave's behavior to a particle's energy. And his first target? The simplest atom there is, hydrogen. Now, to really understand his thinking here, let's use a simple analogy, a guitar string. A guitar string is fixed at both ends, right? So it can't just vibrate any old way. It can only vibrate at very specific frequencies. Its pure tones, its harmonics. Schrödinger had this brilliant realization that an electron bound to a nucleus is a lot like that. It's trapped, so its wave can only exist in these specific, stable patterns. And it worked. It worked brilliantly. His equation perfectly predicted the exact quantized energy levels for the hydrogen atom. We're talking about the precise frequencies of light that it spits out. In fact, these solutions are the atomic orbitals that you probably learned about in chemistry class. But, and here's the absolute crucial point for our mystery, this first version of the equation, the one that didn't change with time, it used only real numbers. Our mystery guess, the imaginary number I, still hadn't made its appearance. The impact was just immediate and profound. Robert Oppenheimer himself would later call it perhaps the most perfect, most accurate, and most lovely theories that man has discovered. High praise, right? But Schrödinger's work, it wasn't done yet. You see, what he had so far was a static picture of the atom, like a photograph. But what he really needed was a dynamic one, a movie. He needed an equation that showed how these matter waves actually evolved over time. And this, right here, is the moment where I was forced to enter the stage. This was the next huge question on the table. Okay, a static wave is one thing, but how does it actually move? How does it change from one instant to the next? To solve this problem, Schrödinger had to do something that even he found, well, deeply unsettling.
Yeah, you heard that right. Even Schrödinger himself was uncomfortable with it. He actually wrote in a letter to another physicist that using complex numbers was, and I quote, unpleasant here and indeed directly to be objected to. He was convinced, deep down, that the wave function had to be fundamentally real. But the math, and ultimately reality itself, told him something different.
Okay, let's just break down how a normal wave moves for a second. Think about a simple wave on a string. The curvature, how much it's bent at any given point, that creates a force that pushes that part of the string either up or down. So more curve equals a stronger push. It's a pretty simple cause and effect relationship.
Now, Schrödinger's matter wave works in a similar way. The spatial curvature of that wave also dictates how it's going to change in the very next instant. But there's a twist, a 90-degree twist, to be exact. Okay, this is it. This is the crucial point. The imaginary number I isn't really a number in the typical sense here. It's acting as a command to rotate. So think of a normal number line, going left and right. Now imagine a second imaginary axis that runs straight up and down, crossing at zero. That's called the complex plane. So instead of the wave's curvature creating a simple push up or down, multiplying by I takes that push and rotates it by 90 degrees on that plane. It's not a quantity, it's literally a command to turn.
And this continuous 90-degree rotation is the magic key. It's what makes the wave function actually move. Instead of just bobbing up and down in one place like a buoy in the water, this constant turning pushes the wave's phase around in a circle. And that circular motion is what makes the entire wave pattern propagate forward through space and time. So that's what I is doing. It's the engine that drives the matter wave forward.
So you might be thinking, okay, that's a clever mathematical trick. But here's the thing. It turns out this complex, rotating wave function isn't just a trick. It is absolutely essential for explaining some of the strangest and most fundamental behaviors we actually observe in the quantum world. I mean, just take the legendary double-slit experiment. You fire electrons one by one at a barrier with two slits, and what do you get on the other side? An interference pattern. It's as if each electron went through both slits at once as a wave and interfered with itself. The only possible way to explain this is if the electron's wave function has something called a phase, basically an angle. And that is exactly what a complex number, managed by our friend I, provides. The great physicist Paul Dirac, he really put it perfectly. He said this phase, this angle of the complex wave function, is the source of all interference phenomena. Think about that. It's a property that we can never see directly, it's totally hidden from view, but it is absolutely essential to the way nature actually works. And I think the physicist Freeman Dyson captured the beautiful absurdity of this whole thing when he called the appearance of the square root of -1 in wave mechanics one of the most profound jokes of nature. It's like nature is telling us that reality doesn't just operate on the simple number line we're used to. It operates in this richer, deeper, complex system that we humans, for the longest time, just dismissed as imaginary. So we're left with this absolutely fascinating thought. A number system that was basically invented just to solve some abstract math problems turns out to be the fundamental language that describes how our entire universe evolves. It really forces you to ask the question, what else about the reality we think we know is just one small slice of a much deeper and far more complex picture?